Welcome, everyone, to another deep dive. Today, we're going to be exploring something that's hidden in plain sight. I bet you've never stopped to think about all the imperfections hiding inside solid materials. You sent us this chapter from a material science textbook, and I have a feeling it's going to totally change the way we look at the stuff around us.
It really is amazing. When we think about solids, we usually picture them as perfectly ordered structures, like a flawless sheet of glass. But the truth is, even the most pristine materials have a whole secret world of imperfections.
Okay, so you're telling me that there are imperfections in solids, like even metals.
Exactly. This applies to all kinds of crystalline solids, metals, ceramics, you name it. It's all about those imperfections, or defects as they're called. And these are just deviations from that perfect atomic arrangement we picture in our minds.
Wow, so you're telling me even something like a diamond with a seemingly perfect surface could have these tiny flaws? It's kind of mind-blowing.
Absolutely. And here's the thing. These imperfections aren't always bad. In fact, they can drastically change a material's properties, sometimes for the better. They can make things stronger or more durable, for example.
Hold on. So flaws can actually be good. I'm having trouble wrapping my head around that. Can you give me an example?
Sure, think about pure gold. It's beautiful, but it's also really soft, right? If you want to make something like jewelry, you need to add other metals like copper or silver. That creates an alloy which is much stronger and more wearable.
Oh, I see what you're saying. So adding those other metals, those impurities, actually makes the gold better in a way.
Exactly. It's all about disrupting that perfect order and making it tougher for those atoms to slide past each other, leading to a harder material. Controlling these imperfections allows us to fine-tune a material's properties.
This is fascinating. Okay, so let's break down these imperfections a bit. Where should we start?
Well, we can start with the most basic type, point defects. Imagine a perfectly tiled floor, but some tiles are missing and some extra ones are crammed in where they don't fit.
So when we're talking about materials, are those missing or extra tiles actually atoms?
You got it. Missing atoms are vacancies. It's just an empty space where an atom should be. And those extra atoms jammed in, those are called self-interstitials. They don't really belong there.
Hmm. I can see how those would mess up that perfect arrangement. But just how common are these defects?
They're more common than you think. Even at room temperature, atoms in a solid are constantly vibrating, which can lead to vacancies. And as the temperature rises, the number of vacancies goes up exponentially. In fact, there's an equation for this in your textbook. It's equation 4.1.
So it's kind of like the atoms are always doing a little dance, even in a solid, and sometimes they just pop out of place.
That's a great way to picture it. And this movement of atoms is exactly why, say, a blacksmith heats metal to shape it. That higher temperature makes more vacancies, making it easier for atoms to move around. And that makes the metal easier to deform.
So heating metal doesn't just soften it, it creates these vacancies so the atoms can move more freely.
Precisely. Now let's talk about those self-interstitials, those extra atoms. They're less common than vacancies, but they can cause a lot of distortion in the surrounding structure, which changes how the material behaves.
So even though they're tiny, those self-interstitials are like little troublemakers, messing things up.
You could say that. They put stress on their neighboring atoms, and that affects things like how easily the material deforms or conducts electricity.
Wow, it's amazing how much impact these little imperfections can have. I'm already looking at the stuff around me a bit differently.
It really does change your perspective. But we've only just scratched the surface here. We have another category of imperfections to talk about. Impurities.
Impurities, that sounds like a bad thing. Doesn't that mean the material is weaker?
Not necessarily. Remember our gold alloy example. Sometimes adding impurities is actually intentional and beneficial. We call that a solid solution.
A solid solution. Is that kind of like when you dissolve sugar in water, but with atoms in a solid?
That's a great analogy. And just like dissolving sugar in water, there's a limit to how much you can dissolve in a solid. And these limits, they depend on things like atomic size, crystal structure, and even the electronegativity and valences of the atoms involved.
Electronegativity and valences. Wow, this is taking me back to high school chemistry.
Don't worry, we'll keep it simple. Electronegativity basically describes how strongly an atom attracts electrons. And valence, that refers to how many bonds an atom can form with other atoms. These factors tell us how well different atoms mix together in a solid solution.
Okay, so it's like a matchmaking game for atoms, seeing which ones get along.
Exactly. Now, these solid solutions, they can either be substitutional or interstitial. In a substitutional solid solution, impurity atoms replace the original atoms. In an interstitial solid solution, the impurities squeeze into the tiny gaps between the original atoms.
So are we back to talking about missing or extra tiles again?
Yeah, you could think of it that way. But now we have different kinds of atoms mixed together, not just missing or extra atoms of the same type. Take sterling silver, for example. It's actually an alloy of silver and copper. The copper atoms replace some of the silver atoms, making it much stronger.
Ah, so that's a substitutional solid solution.
Yeah.
What about interstitial?
A great example of that is steel. Carbon atoms are pretty small, so they can fit into the spaces between iron atoms. That's what makes steel so strong.
Steel.
Uh-huh.
That's incredible. It's amazing how these tiny changes in the atomic level can completely transform a material's properties.
It really is. But it's not enough to just know what kinds of impurities are in a material. We also need to know how much of each element is present. That's where weight percent and atom percent come in.
So weight percent is like saying for every 100 grams of this alloy, X grams are iron and Y grams are carbon.
Exactly. It's just a simple way to show how much of each element is there, based on weight. But sometimes we need to be more precise, especially when dealing with tiny amounts of impurities that can have a big impact. That's when we use atom percent.
So atom percent looks at the proportion of each element based on the number of atoms, not their weight.
That's right. You can find equations for calculating both weight percent and atom percent in your textbook. They're equations 4.3 and 4.5. These calculations are really important in fields like semiconductor manufacturing, where you need to control impurities very carefully because they can have huge effects on the material's electrical properties.
So it's not enough to just know what's in there. You need to know exactly how much of each element is present. Kind of like a recipe, but for atoms.
Precisely. Getting the proportions just right is key to creating a material with the desired properties.
Wow, we've gone from missing atoms to extra atoms, from pure materials to intentionally adding impurities. Are we done talking about imperfections, or are there more surprises?
Oh, there are definitely more surprises. We haven't even gotten to line defects, also called dislocations.
Line defects. So instead of just one atom being out of place, it's a whole line of them. That sounds like it would be really disruptive.
It can be. Imagine you have a line of bricks that are all perfectly aligned. Then suddenly there's a shift in the middle. That's kind of what a dislocation looks like in a crystal lattice.
I can picture that. But how do these dislocations actually form in a material? And what kind of effect do they have on its properties?
Those are excellent questions, and they take us into the fascinating world of different types of dislocations and how they behave. But that's a story for the next part of our deep dive.
Welcome back. Just before the break, we were talking about these really cool line defects. Dislocations. It's kind of like a shift or even a wrinkle in the otherwise very ordered arrangement of atoms.
Right, those shifted bricks you mentioned. I can kind of picture that in my head, but it's hard to imagine how something like that happens on such a small scale, at the atomic level. What exactly causes these dislocations to form? Well, just think about what happens if you were to bend a metal paperclip. You're not actually breaking the metal. You're causing those planes of atoms to kind of slide past each other. That movement, that's actually made possible by dislocations forming and moving.
Oh, that's interesting. So these dislocations, it's like they're little cracks that allow the material to change shape permanently without completely breaking apart.
That's a good way to think about it. Okay, maybe not cracks exactly, but they are points of weakness, in that crystal structure. And those weak points, those dislocations, make it easier to bend and deform the material without it actually breaking.
Fascinating. So you mentioned earlier that there are actually different types of dislocations. What makes them different?
Okay, so the two main types are edge dislocations and screw dislocations. Let's start with edge dislocations. Imagine you're looking at that, that perfect crystal lattice. Now, picture an extra half plane of atoms inserted into that perfect lattice. That creates a sort of step right there in the structure.
So it's like if you were building a wall with bricks and you suddenly added an extra half brick in one of the rows.
Yeah.
It would throw off the whole alignment, right?
That's exactly it. Now, with a screw dislocation, imagine you take that same perfect crystal lattice and you give it a twist. Like the planes of atoms kind of spiral around this line, this dislocation line, like a staircase. It's a little harder to picture in your head, maybe, but you can get the general idea of this twisting distortion happening in the lattice.
Okay, I think I'm starting to get it.
Yeah.
So how do these different types of dislocations actually affect a material's properties? I mean, do they make a big difference?
Oh, yeah, definitely. The way those dislocations move and interact with each other plays a huge role in how a material responds to stress. For instance, think about how a material bends. If there are lots of dislocations that can move easily, then that material will be more ductile. That means it can bend into form without breaking. But if a material doesn't have many dislocations, or if they get pinned in place, then it will be stronger but more brittle.
So if you can control these dislocations, you can fine-tune how strong and flexible the material is.
You got it. And that's why understanding dislocations is so important in material science. There are actually all kinds of processing techniques like work hardening and heat treatments that can manipulate those dislocations and create materials with specific properties we need.
Makes sense. Okay, so we've talked about those point defects and impurities, and now we've covered dislocations. I feel like every time we zoom in on a material, we find a whole new level of complexity. Are there any other types of imperfections we should be aware of?
Oh yeah, for sure. We also have interfacial defects. These are basically boundaries between different regions inside a material.
Boundaries, you mean like lines drawn within the material? I'm not sure I understand. What kinds of boundaries are we talking about?
Well, the most obvious boundary is just the external surface of the material. Now, it may seem strange to think of a surface as a defect, but if you look at it from the perspective of that perfect crystal lattice, it is definitely a disruption.
That's interesting. So at the surface, that perfect order just ends, right? That leaves all those atoms on the edge kind of exposed.
Exactly. You see, those atoms at the surface, they have fewer neighbors to bond with, which makes them more reactive and gives them higher energy. And that higher energy is exactly why surfaces play such a huge role in things like corrosion and catalysis.
Oh, that makes sense. I bet that's why things rust. Those exposed atoms on the surface are just more likely to react with oxygen in the air.
You nailed it. That higher energy state also makes surfaces super important for things like adhesion and friction.
Okay, so surfaces are one type of boundary. What other kinds of boundaries are there inside a material?
Well, another very common type is called a grain boundary. Remember when we talked about those polycrystalline materials? These materials are made up of lots of tiny little crystals or grains, all stuck together.
Yes, I remember.
Yeah.
It's like the material's made up of a bunch of tiny crystals, like a mosaic, instead of just one big crystal.
Exactly. Now, those boundaries between those individual grains, those are grain boundaries. In those regions, the crystal lattice doesn't line up perfectly, you see, which leads to that higher energy state again.
Oh, I get it. So it's like those shifted bricks we talked about, but on a much bigger scale, with entire groups of atoms not lining up perfectly.
You got it. And just like other imperfections, these grain boundaries, they can make a big difference to the material's properties. In general, smaller grains can improve ductility. Even the orientation of those grains matters because it influences how the material reacts to stress and strain.
So the way those tiny crystals fit together or don't fit together perfectly is another big factor in determining how the material behaves overall.
Exactly. That's why controlling those grain sizes and orientations is so important when we're making materials.
Wow. It's making me look at the metal spoon I'm holding in a whole new way. It's not just a solid object. It's like this complex landscape of all these tiny crystals and all these little boundaries.
That's a great way to put it. And there are even more types of boundaries you can find inside materials. There are phase boundaries, where different phases of a material come together. There are twin boundaries, where the crystal structure is mirrored, and then you have stacking faults. These are just interruptions in how the atoms are stacked.
Wow, there's so many different types of boundaries, and each one with its own quirks. It's amazing how much is going on inside something that seems so simple at first glance.
It really is. But don't forget, we still have one more category of imperfections to go. Bulk defects.
Bulk defects. That sounds like we're going up a whole level now, compared to those point defects and line defects. What kind of things count as bulk defects?
Well, for these, we need to think bigger. Bulk defects are things like pores, cracks, foreign inclusions, anything that disrupts that material structure on a larger scale.
Okay, now those sound like they're definitely flaws, not features. I'm guessing we don't want to see those in our materials, right?
Well, it depends. While they can weaken a material, sometimes we actually want to introduce these bulk defects on purpose to create a material that has special properties. For example, if you want to make a lightweight structure, you could incorporate some porosity, some tiny holes. Or you could add certain inclusions to make the material stronger or more resistant to wear and tear.
Oh, so sometimes these large-scale imperfections can be helpful. It really highlights that a perfect material doesn't always exist, right? It's more about figuring out how those imperfections, big and small, can be used to make a material behave the way we want.
Exactly. It's all about understanding how these imperfections work. And to do that, we need ways to actually see them. That's where microscopy comes in.
Right. I mean, we can't just look at a piece of metal and see these tiny defects with our eyes.
Yeah.
What tools do scientists use to actually see them?
Well, there's a whole range of microscopy techniques out there, and they each have their own strengths and weaknesses. Some of the most common ones are optical microscopes, electron microscopes, and scanning probe microscopes.
Okay, tell me more. How do these microscopes work? And what exactly can they show us about these hidden imperfections?
All right, let's start with something you might be familiar with. The optical microscope. It uses visible light to magnify the structure of a material, and it's a great tool for examining surfaces and finding things like those grain boundaries and any larger defects.
Oh yeah, I remember using those in biology class. But I'm guessing we need something a little stronger to see those tiny point defects and dislocations, right?
You're right. For those, we need to bring in the big guns. Electron microscopes use beams of electrons instead of light. And because electrons have a much shorter wavelength than visible light, they can resolve much finer details, allowing us to see things at the nanoscale.
Wow, so it's like using a camera with super high resolution to zoom in on the atoms themselves.
Pretty much. There are two main types: transmission electron microscopes, TEMs, and scanning electron microscopes. The TEM sends a beam of electrons through a thin sample so we can see its internal structure and those internal defects. The SEM scans a focused electron beam across the surface, creating these really detailed 3D images.
So it's like the TEM gives us a slice through the material, and the SEM gives us a super detailed surface view. They both sound incredibly powerful. Are there any other types of microscopy we should talk about?
There's also a newer group of microscopes called scanning probe microscopes, or SPMs. These microscopes are super versatile. They use a tiny little probe to scan the surface of the material, and get this, they can create images with atomic resolution.
Atomic resolution, that's crazy. What kind of information can we get from these SPMs?
Well, they can show us the topography of the surface, the hills and valleys, but they can also tell us about things like electrical conductivity, magnetic fields, even the forces between individual atoms.
It's like having a tiny little fingertip that can feel the surface of a material at the atomic level. So with all these different microscopy tools, we can literally see those imperfections and understand how they impact the material's properties.
Exactly. By studying these images, we can learn a lot about how materials behave and how we can manipulate them for specific uses.
This is incredible. We've covered so much ground. Point defects, dislocations, grain boundaries, bulk defects, and now microscopy. I'm starting to wonder, why is all this so important? How does understanding these imperfections actually change things in the real world?
That's a great question. It gets to the heart of why materials science matters so much. These imperfections, these little flaws, are actually the key to unlocking a material's potential. They influence so many things, from a material's strength and flexibility to its ability to conduct electricity and even interact with light.
So it's not about making perfect materials. It's about understanding and controlling these imperfections so we can design materials for specific purposes.
You got it. By figuring out how those imperfections work, we can make lighter and stronger alloys for things like airplanes. We can make more efficient solar cells, and even create biomaterials for medical implants. There's just so much potential.
This has been such an eye-opening experience. I feel like I'm seeing the world in a completely new way. Even the most flawless-looking objects are full of these little imperfections that define what they are.
It really is a humbling thought, right? And it shows just how complex and beautiful the materials that make up our world truly are. But we're not done yet. There's one more interesting thing about imperfections. I want to talk about how they play a role in a phenomenon called catalysis.
Catalysis. Oh yeah, I remember the word from chemistry class, but it's been a while. What exactly is catalysis, and what do imperfections have to do with it?
Let's talk about that after a short break. We'll explore how those tiny imperfections, especially the ones on a material's surface, can act like little chemical factories, driving all kinds of important reactions that have a huge impact on our lives.
Okay, so before the break, we were starting to talk about how these little imperfections we've been discussing can actually play a role in something called catalysis. It sounds like we're shifting gears from, the structure of materials to the world of chemistry now.
Yeah, that's right. Catalysis is all about speeding up chemical reactions. And those imperfections, especially the ones found on surfaces, they can be really important in that process.
Okay, remind me how catalysis works again. I vaguely remember it from chemistry class, but it's been a while.
Well, in simple terms, a catalyst is just something that helps a chemical reaction go faster, but doesn't actually get used up itself. Think of it as a matchmaker, bringing the reactants together in the right way so the reaction can happen more efficiently.
Okay, I'm starting to remember now. So how do those imperfections fit into this picture?
A lot of catalysts are actually solid materials, and it's the imperfections on their surfaces that create these active sites where the reaction happens. The missing atoms, the extra atoms, or even just the unique arrangement of atoms around these boundaries. They can create special environments that attract and hold those reactant molecules, giving them more chances to interact and react.
So it's like those imperfections create these little meeting points or hot spots where the reactant molecules can bump into each other more easily and react.
That's a great way to think about it. And this whole thing, surface catalysis, it's super important in so many different applications, from industrial processes to environmental technologies.
Okay, now I'm really curious. What are some real-world examples of where this is happening?
One of the most common examples is the catalytic converter in your car.
Oh yeah, those catalytic converters.
Yeah.
I know they're supposed to, reduce those harmful emissions from cars, but I never really understood how they actually worked.
It's all about surface catalysis. So inside a catalytic converter, you have this ceramic honeycomb structure, and it's coated with these precious metals like platinum, palladium, and rhodium.
Precious metals. I bet that's why those catalytic converters are so expensive.
You got it. Those precious metals are important because their surfaces are covered in tiny imperfections that act as those active sites. And those sites are what convert the harmful pollutants into less harmful substances.
So those tiny imperfections are basically tiny chemical factories that turn pollutants into harmless stuff.
That's a really good way to think about it. For example, carbon monoxide, that's a poisonous gas, right? Well, the catalyst helps turn that into carbon dioxide, which is much less harmful. And then you have nitrogen oxides, which contribute to smog and acid rain. The catalyst breaks those down into just nitrogen and oxygen.
Well, so it's like these imperfections are actually helping to clean up our air. Are there other examples of surface catalysis being used to, benefit the environment?
Absolutely. It's also being used to create cleaner fuels, remove pollutants from water, and even to develop new energy technologies like fuel cells.
This is incredible. It really shows how something we might think of as a flaw, something imperfect, can actually be really useful, even essential. It really changes how you think about the whole idea of what perfect means.
It really does, and it just goes to show you how important it is to really understand things at their most basic level. Often it's those little details, those hidden things, that have the biggest impact on how things actually work.
Well, I have to say, this has been an amazing deep dive. I feel like I've gained this whole new appreciation for the materials all around us and the fascinating world of imperfections hidden within them.
It's been my pleasure exploring all this with you. And remember, next time you look at anything at all, whether it's a simple spoon or a complex machine, just think about all those atoms and imperfections inside, all working together to give that object its properties and behavior.
Thanks again for taking us on this deep dive. I'm already looking at the world around me in a completely new way. And to all our listeners out there, thank you so much for joining us. We hope you've enjoyed this journey into the hidden world of imperfections. Until next time.